All right, so in the last video, we sort of gave a motivation for the idea of a sum of two vectors, at least geometrically speaking. So in that example, we put two forces together and it created a rectangle. But in this specific case, that only happened because the two forces were perpendicular to each other, so they formed a right angle here. They don't need to be that way. They can have some other angle between them. And in that case, I can come up with a very similar idea behind the sum of two vectors by thinking in terms of a parallelogram. So let's suppose that this here is vector u, and this here is vector v. Now suppose I were to take u and copy and paste it so that the initial point of u will now coincide with the terminal point of v, like this. And then I do the same thing with v, copy and paste it so that its initial point coincides with the terminal point of u. What it creates is this parallelogram. If I take the original initial point that the two vectors had in common, and if I created a new vector that has that same initial point and whose terminal point is the common terminal point of these two vectors, then this is what I would think of as the vector u plus v. Okay, now let's look at the relationship between this geometric idea of adding two vectors and the component form of u and v. So now let's take both of these vectors and make them position vectors. Let's suppose that this is my vector u, but I'm going to give it components. So I'm going to call it a1, b1. That would mean that the base of this right triangle that I'm creating here is a1, and the height is b1. Okay, now I want to add another vector to it. Notice that even though I created a parallelogram in here, I kind of didn't need to create the entire thing. It would have been enough to just take the vector v and have its terminal point coincide with u's initial point. Sometimes people call this tip to tail. So if I call this terminal point the tip of u, and then I overlap it with the tail, the initial point of v, together these two can be joined to make the resultant vector u plus v. So in this diagram, I'm not going to create the full parallelogram. I'm just going to draw each vector tip to tail. So let's suppose that here's the second vector, the one that I want to add to it. And let's suppose that it has components a2, b2. Okay, so think about what that would represent. That means that the base of this right triangle, which would be the same as this length right here, is a2. And the height of this right triangle, this part right here, would be b2. Now notice if this is b1, then so is this. And the resultant vector, this one here, is going to have a horizontal component that is made up by the sum of these two values, and a vertical component that's the sum of these two values. So in other words, if you want to add two vectors and you know their component form, then we do it by what's called component-wise addition. If u is equal to a1, b1 and v is equal to a2, b2, then the sum of the vectors, the resultant u plus v, is going to have a component form a1 plus a2 and a2, I'm sorry, that should say a1 plus, and that part's correct. This should be a b1 right here. That's a mistake on my part. b1 plus b2. That's what we're going to see there. Okay, so that's the concept of vector addition. We have two other operations that we want to define. We're going to start with scalar multiplication and then combine that with addition to come up with a concept of subtraction as well. So scalar multiplication is what happens if we try to multiply a vector by a real number. Notice I'm not multiplying a vector to another vector here. I'm multiplying a vector to a number. That number is going, in this case, we're going to start by thinking of it as a positive real number, but we'll talk about non-positive numbers as well. And we call this real number a scalar. I'll make sense of that terminology in a second. So if v is a vector and k is a scalar, then we can multiply v by k to create a new vector And this vector is going to have the same direction as v, but its length or magnitude will be k times the magnitude that v was originally. Okay? So essentially what that means, and here's where I make sense of that term scalar, multiplying v by the scalar k simply scales v by a factor of k without rotating it. That means without changing its direction. Again, we're assuming k is positive here. So these three arrows right here give an idea of what I'm talking about. It's a little bit small, but this orange arrow right here is the original arrow v. If I multiply v by the scalar 3, which I can call that 3v, that produces this vector. Notice this vector has the same direction that v had, but it's 3 times the length, 3 times the magnitude. If I multiply v by 1/2, for example, then that would still give me a vector with the same direction, but it would give me half the magnitude that v has. Okay, so that's what multiplying by a positive scalar does. Keeps the direction the same, but stretches or compresses that vector by whatever factor k gave us. What if k is a negative number? Well, the way we interpret that is kind of similar to how we think of r being negative when we're talking about polar coordinates. It has a similar effect, but what it does is it rotates the vector or flips its direction around. So for example, here, no, actually, let me come back to this. In the event that k is equal to -1, so if we multiply a vector v by -1, we oftentimes don't write the -1, we just say negative v. And all that would do is flip the vector completely around. So notice here, v points this direction. Negative v has the same length that v has, but is pointing in the opposite direction. So basically, it just traded initial and terminal points. If I multiplied by -2, for example, then what that would do is flip the direction of v like this, and then scale it by a factor of 2, so it would have double the magnitude. Okay, so that's the effect that multiplying by a negative scalar has. If you multiply a vector by the scalar 0, which I didn't write about on here, that always gives us the 0 vector. Okay, because that's like multiplying the magnitude of a vector by 0, giving us a magnitude of 0. So, with that said, now we can make better sense out of subtraction. Let's suppose you have these two vectors, u and v, and we want to subtract them, u minus v. We define subtraction this way. U minus v is equal to u plus negative v. And geometrically, we're going to make sense of that down here. So let's suppose I have a vector u. Here's u, and let's suppose this is v. Okay? The difference between u and v, so u minus v, is going to be interpreted as u plus negative v. So if I have v sketched out here, I should determine what negative v looks like. So I want to keep the magnitude the same, but I want to flip the direction. Here's negative v. Okay, and then how do we add u plus negative v? Well, the definition of addition says that I create a parallelogram. So I would take negative v, this vector, copy and paste it so that its initial point coincides with the terminal point of u, like this, and then have u copy and paste it as well so that the initial point of these two vectors coincides with the terminal point. Okay? Now, that's let me write that here. This is u minus v. Notice that it creates a parallelogram. What I'd like to do is kind of relate that parallelogram back to the original two vectors that I drew, u and v. Notice that this would be u down here as well. And even though this is negative v, it has the same magnitude that this v has. So this parallelogram could be copied up here, and I could reuse these two vectors. Let me do that over here. So here's my original u. Here's my v, and if I copied that parallelogram, whoop, didn't draw that very well. Then what I'm seeing in this parallelogram down here is that the difference between u and v is a vector that makes up the other diagonal, u minus v. The other diagonal of that parallelogram. This was not drawn very well, but hopefully that gives you the right idea. Notice that u plus v would be this diagonal. So basically, the sum and the difference of u and v represent the two different diagonals of this parallelogram that I get by giving u and v the same initial point. Okay. Notice also that in the case of u minus v, the vector points in the direction of the first vector in this subtraction. So u minus v, u minus v will point in the direction of u. It'll point towards the terminal point of u here, if I'm using this kind of a diagram. All right. Now, if we're trying to evaluate sums, differences, and scalar products, so scalar multiplication with vectors, we need to know how to do that with the component forms of those vectors. We've shown what that looks like using diagrams and graphs and things like that, sketching the vectors out. But what if we're given a vector in component form? How do we do scalar multiplication and subtraction in component form? Well, it works pretty much the exact way you would expect it to. If u is equal to a1, b1, and v is equal to a2, b2, let's suppose first that I want to multiply u by the scalar k. And k could be positive, negative, or 0. This will work in all those cases. Then what I'm doing is just multiplying the components by k. We could show graphically why that's the case, but it's not too difficult to picture that. Similarly, if I want to do u, this should be u minus v. That should be a minus right there. Then I'm just taking the components of u and subtracting the corresponding components of v. I did a little copy and paste here earlier. I'm seeing that I made that same mistake that I made before. This should say b1 right here. I'll correct as I go. Okay. So to do an example, let's suppose that we want to find 4u plus 3v. Notice it's a combination of scalar multiplication with addition. I'm going to mention this term a little bit later, but when we do something like this, if I have vectors that I multiply by scalars and then sum the results, we call that a linear combination of these vectors. So this is what's called a linear combination of u and v. That's a really, really important term in linear algebra, which some of you will take much later down the road. To do this, 4u plus 3v. So 4u, I know that u looks like this, negative 4, 6. That's given to me in the problem. Plus 3v, that's 5, 0. Okay. Think of scalar multiplication as kind of like the distributive property. And order of operations holds here as well. We do multiplication before we do addition. So I have to bring the 4 and the 3 into the components of these vectors. 4 times negative 4 is negative 16. 4 times 6 is 24. And I'm adding 3 times 5, that's 15. 3 times 0, that would be 0. Negative 16 plus 15 would be negative 1. 24 plus 0 is 24. Okay, so we oftentimes are performing multiple operations on vectors at a time. Scalar multiplication and addition in this case. But it's all very straightforward. If you know the rules, it's really just super basic arithmetic. Okay. Moving on. We're going to talk about unit vectors. The term unit in math generally means 1, the number 1. So when we talk about a unit vector, what we're talking about is a vector whose magnitude is 1. Now we can find all sorts of unit vectors in all sorts of different directions, but there's two really important ones that we single out. One is the vector I, which is in component form 1, 0, and the other is the vector j, which in component form looks like 0, 1. Let me show you what those look like. I is the vector 1, 0. That means it's horizontal. I'm going to put these in standard form, or standard position, by the way. It has a horizontal component of 1, so from the origin I move 1 unit to the right, and a vertical component of 0, which means I don't move vertically at all. So the vector I is right there. Notice it's on the x-axis, okay? Similarly, j has 0 for its horizontal component, but 1 for its vertical component. So j is there. So together they sort of lie on the coordinate axes, the x and y coordinate axes, specifically the positive x and y coordinate axes. Now, one thing that we use these unit vectors for, which, by the way, together, if we make a set out of these, and we talk about the set of these two vectors, we call them the standard basis vectors. Not a term that we're going to use much in this class, but it's extremely important in Calculus 3 and linear algebra. Any vector can be represented as a sum of scalar multiples of these guys, or in other words, a linear combination, like I said before. And to see why, let's suppose we have just any vector that's been put in component form, AB. Notice that AB is the same thing as A0 plus 0B. If you add these component-wise, you'll get AB. Not similarly, but as a follow-up step, A0 is equal to the scalar A times the vector 1, 0, which again, do the reverse. If I were to perform the scalar multiplication, I would get A here and 0 here. 0B is the same thing as B times 0, 1. Notice that 1, 0 and 0, 1 are those vectors that we defined up here. So this can be represented as AI plus BJ. That's just an alternative notation for this exact same vector here. And notice the components, A and B, show up as scalars being multiplied to the vectors I and J respectively. Okay, so geometrically, here's what's happening. Notice I and J are on the X and Y axes specifically. If I want to represent the vector V as a linear combination of I and J, AI plus BJ, what it's doing is it's taking the vectors I and J and scaling them by A and B, so it stretches or compresses them depending on what A and B are. It may flip the vectors if either A or B are negative. And then summing those two, tip to tail, it gives me this vector here, which I can think of as like the... I can think of this as like the hypotenuse of this right triangle. Notice that because this is in standard position, this terminal point would be AB. Okay. So let's look at performing some operations. Now again, if you notice the component form of this vector, AB, relates directly to the scalars that I'm seeing here. And these are just two representations for the same vector. So if I want to perform operations on these vectors, it works the same way. Notice U is equal to 3i minus 5j. And V is equal to negative 2i plus 4j. So if I want to find negative 10u minus V, that's negative 10 times 3i minus 5j minus negative 2i plus 4j. And at this point, you can really just think of the I and j like variables. And it's essentially just performing some algebra, combining like terms. This would be equal to, after distributing the negative 10, negative 30i plus 50j, distributing the minus sign in here, positive 2i minus 4j. Think of it as combining like terms now. Negative 30i plus 2i, that would be negative 28i. And then 50j minus 4j is like plus 46j. That's the same thing I would have gotten if I had represented these in component form. It's just, it would look like, you know, the component form for a vector, but the components would be negative 28 and 46. Okay. This notation, it may seem a little bizarre that we would want to have a different representation for vectors when it's really kind of conveying the same information that component form does. But the reasons behind representing these vectors the way that we're doing it here become much more apparent in courses like Calculus 3 and linear algebra. It's actually very useful notation for some stuff you do in those classes. All right. So far, on the topic of unit vectors, the only unit vectors we've dealt with have been those standard basis vectors. And those are very important, of course, but we can talk about unit vectors that have some different direction than those two. So oftentimes, what we're doing is we're being given a vector v, and we're going to be asked to find a unit vector that has the same direction as v. Or we'll just say the unit vector in the direction of v. That's how we oftentimes say that. We're going to show that this little formula here will always produce that. So basically, I'm going to use this notation, v divided by the magnitude of v. Before going through this, v is a vector. Remember, the magnitude of v is a scalar. It's a quantity that represents length. So this is like taking a vector and dividing it by a scalar. But notice we haven't defined an operation called scalar division. So really what this is it's just a more convenient notation for this, which is actually scalar multiplication. 1 over the magnitude of v times v. That's a scalar times a vector. All right. Now, what I'm saying here is that if you do this, if you perform this operation on the vector v, in other words, multiply it by the reciprocal of its magnitude, it will always produce a unit vector. That is a vector with a magnitude of 1. And we're going to prove why that happens down here. So let's suppose that you have a vector that's been put in component form. It has components a and b. From our formula for computing the magnitude of a vector, we know that the magnitude of v is the square root of a squared plus b squared. All right? So what does this vector look like using what we just found? Well, v over the magnitude of v literally means we are multiplying the vector v, which is ab, by the reciprocal of this magnitude. But what that does is it just divides each individual component by that magnitude. So this vector here is a over the square root of a squared plus b squared, b over the square root of a squared plus b squared. Now, again, remember what we're trying to show here. We're trying to show that this is a unit vector. So this new vector that I just came up with, which again is going to have the same direction as v, because multiplying v by a positive scalar does not change its direction, as we've seen. But I want to show that the magnitude of this is equal to 1. So having computed this, I now need the magnitude of this new vector. Well, the magnitude of this vector is the square root of the sum of the squares of these components. And if I square these components, the radicals go away, and I get an a squared and a b squared in my numerators. Adding these together, my numerator becomes a squared plus b squared over a squared plus b squared, which is, of course, equal to 1. The square root of that is equal to 1. Okay. Now, the only case where this wouldn't work is if both a and b were equal to 0, because that's the only case where I would get a 0 in my denominator down here. But that's a non-issue. Why is that a non-issue? Well, if a and b are both equal to 0, then v would have been the 0 vector. But 0 vector, like we said, the 0 vector does not have a direction. So it doesn't make sense to find a unit vector in the direction of a vector that doesn't have a direction. So in other words, this doesn't apply to the 0 vector, but it applies to all other vectors. So let's go through an example. I want to find the unit vector in the direction of -3, 8. The first thing I want to do is find the magnitude of that vector, because that's what I'm going to be using in that formula, -3, 8. Okay? So this is equal to the square root of the sum of the squares of my components, -3 squared plus 8 squared. All right, so 8 squared, that's 64 plus 9 is what I would get here. 64 plus 9 would be 73. I get the square root of 73 here. That means in component form, if I want to find my unit vector, I'm multiplying 1 over root 73 to my original vector, -3, 8, giving me this. -3 over root 73, 8 over root 73. And that's my answer. I'm going to point something out about this answer as well. You notice I did not rationalize these components. We make kind of a big deal about rationalizing fractions earlier in this course. My reasoning for emphasizing that is because it reveals some useful patterns that help with remembering the unit circle, especially when we're talking about radian measure and stuff like that. But beyond that, there's actually not much reason to bother rationalizing fractions anymore, rationalizing denominators, at least if they're scalars. There is some usefulness when these are expressions involving, variables like x or something. You'll see that in calculus when you're evaluating difference quotients. It becomes kind of useful there. But beyond that kind of stuff, there actually isn't a huge problem leaving a radical in your denominator like this. In fact, when you get to those courses like calculus 1, 2, and 3, they stop rationalizing these completely. So I'm going to say that for the purpose of these sorts of problems, you oftentimes end up with radicals in your denominator. Don't worry about rationalizing those. It's not going to really matter. Okay? We have a little bit more to cover, and we'll do that in the next video.